Hi, welcome to tutorial number 3 in Power Electronics module. Today we have some questions covering the DC-DC converters, buck and buck boost converter. My advice is to look at the questions first, practice them and try them. If you struggle in any part, you can look at the answers and also follow the step-by-step answer in this video. So let's now start with the first question. So the first question is covering the buck converter. That's why we have on the right here the collection of all the derived relations for the buck converters from the slides. And this is what we usually have if we want to solve any question for the buck converter and design the components. So now let's start looking at the given question now. So the problem number 1 is design a buck converter, including the output filter with the following specification. We have an input voltage of 48, so that's why we have here Vn equals 48 volt, and we have output voltage 18, so we have Vout equals 18 volt. We have the frequency of switching 40 kilohertz, and then finally the load is 10 ohm. I advise you to remember also the circuit itself, because it helps you to really figure out the currents for each part as we explained in the lecture. So that's why I'm going just to sketch the circuit, which is here positive negative for the source, and then we have here a switch. Okay, that's the, for example, an IGBT, and we have here a diode and an inductor and then capacitor, and finally we have a load. So that load, it seems 8 ohms, okay? We have L, we have C, we want to design them, we have the diode, and we have the switch. So what is the remaining? Now, the inductor current peak-to-peak rebel, delta IL equals 80%. So delta IL now equals 80% of the DC component. But do we know the DC component? Until now, we don't know. Okay, so of the DC component. So what is the DC component? We know that this inductor here, okay, has a waveform like that, okay, and that waveform is DC component will go to the output like this, okay, and that rebel will be filtered by the capacitor. So the IC here, okay, if we want to know the IC, it will be like that. So this is the rebel, will be filtered by the output. Your understanding of what's going on, it makes easier to understand the question and also to solve it. Okay, now let's continue with about the output peak-to-peak rebel. It's 0.5% of its DC component. Again, we have Vout and delta Vout equals 0.5% of the DC component. Now, if the converter is considered to be ideal, that means the losses for the diode and the IGBT or the switch is 0. So what are these requirements here? The duty cycle, the inductor value, the output capacitor value, and also the semiconductors devices ratings. If we want to select one of the switches, which one and what capabilities of voltage and current should handle. So now let's start with the solution. So the duty cycle, buck converter duty cycle, I think all of us look at the right, we have this law here, okay? Duty cycle is known if we know the V output and V input. And yes, we know the V output and V input there and there, okay? So I think the duty cycle is very easy. Duty cycle will equal the V output divided by the V input from that question. So from that equation. So we have the V output to be 18 divided by 48, and that will bring 0.375. And now the second question is about the inductor value. And I think the equation that has the inductor is this one, I believe. Okay, so because we have delta IL, so we have here A and we have here B. Delta IL equals delta, which we know delta, the duty cycle, 1 minus delta, we know it so far. V input is known as well, divided by the frequency and the inductance. We don't know the inductance, but we know the ripple, okay? So we know the ripple, but the ripple is percentage of the DC component. But do we know the DC component? So the DC component here is the same as the output current going from through that load, okay? So we want to know what is the V output and the resistance, and I think we know the output current. So the output current equals the V output divided by the load, okay? And I think we know the V output, which is 18 volt here. So 18 volt divided by 10 ohm, and that will give us 1.8 ampere. So this is the DC component will go through my load. So what is the ripple now? The ripple says there that the ripple is 80% of that DC component. So my ripple now, delta IL, will equal 80% of the 1.8 ampere, and that will give us 1.44 ampere. This is our ripple. So now I think I can get this value and just substitute it in that equation, and I can get L to equal delta, which is 0.375, 1 minus 0.375, multiplied by V input, which is 48, divided by F, which is 40 kilo, multiplied by delta IL, which is 1.44 ampere, and the result is 195.3 microhenry. This is the inductance needed to make that ripple. But there is a question here. Is that inductance guaranteeing for me the continuous conduction mode, or that will result discontinuous conduction mode? I think the question says here the ripple is 80% of my DC output. So that means if we want to just draw it to understand what is the meaning for that. So I have my I output here, okay, which is 1.8 ampere, okay, and the ripple is 1.44, which is 80%. That means it's going up and down, and the peak to peak there is 1.44 ampere. That means half of that will be from here to there, and the other half from there to there. Which is 0.72 ampere here, okay? That means it doesn't reach the zero. That means we are in continuous conduction mode if we supply the 1.8 ampere. But if we reduce it that more and more to maybe less than 0.7 ampere, that means now this point will touch my 0 point, and maybe I will start going to discontinuous conduction mode. By knowing this value, I think you can estimate how much current, output current, I need to maintain or I need to deliver to keep myself in the continuous conduction mode. And I think by this calculation, now we might know the value of the top ripple here and the value of the bottom ripple here. By what? We know the middle point, which is 1.8. So this point is 1.8 minus 0.72. And that value is 1.8 plus 0.72. And this is very important just to make sure that we know all the values. And it's very important because we are going to select some switches. And that switch should handle the maximum current we calculate in our circuit. So what is next now? I think the next question is about the capacitor value. And I think the capacitor value means we can use this equation. So now let's just write it. Okay, so delta V output will equal delta IL divided by 8FC. Okay, so I think we know all these values and we can really compute C. We know that delta V output, it says in that part here, it says it's 0.5% of the DC output component. What is the DC output component? It's the same as output voltage, okay? So that value will be 0.5% of the output voltage, which is 18 volt, okay? And that will give us a value of 0.005 times 18 equals 0.09, okay? So now the capacitor will equal delta IL, which is 1.44 from the previous branch, multiplied by 8 times 40 kilo times the delta VC, which is 0.09. And that will give us a value of 50 microfarad. And now let's go to question number D. It says, what is the semiconductor device's ratings? And what we mean by this, that switch and that diode, okay? I think we need to know what is the maximum voltage can be applied across the terminals of each to specify the ratings, okay? So I think the value of the current going from the source through the switch and going to the load, I think it's the same as the current going to the inductor. And in the second off time, so we have, this is on time, and in off time, that current, which is the current of the inductor, also will go and return back to the diode. So both the switch and the diode should have the same inductor current and the maximum inductor current. We have seen here, okay, that the maximum inductor current, the maximum of the maximum, is this point here, okay? And that point is 1.8 plus 0.72. That means it equals 2.52. So this is the maximum current. So maximum current should go through the diode and the switch equals 2.52 ampere. Okay. What about the maximum voltage? And that's for the diode and also the transistor. What about the maximum voltage? I think when this switch now, look at this switch, okay, when it is off, okay, so what is the voltage at that point and what's the voltage at that point? And this is the maximum voltage can be applied across that transistor. So that point here will equal V input, which is 48 volt, and that point, if that if the diode is on, that means it's shorted to the ground, that means it's 0. So the maximum voltage should be 48 volt for the transistor, maximum voltage here for the transistor, and also for the diode. When the transistor is on, the diode will be off, and if the diode is off, we can find the maximum voltage between that point as well and also that point, okay? So this will happen if the transistor is on. That means that point on the top here, it will be the same as the V input, which is 48, and that one is already the ground. So again, we have also 48. So this is also for the diode. Okay, but these are the maximum stresses applied across the terminals of each switch. But if we want to select, we have to multiply this by some fractions, maybe 50% or another 100%, and that will give us selection range of the switches that might be suitable for this application. And I think by this we have finished question number 1. Let's go now to question number 2. Now in the second question, we have to design a boost converter with the following specification. So we have the input voltage 12 volt and the output is 30 volt. And the switching frequency is 40 kilohertz with the resistive load of 50 ohm. So it says here we have to maintain continuous operation. Okay, so we have continuous conduction mode. The ripple is 80% of its DC component. So we need to know the DC component going to the output, and we take 80% to the as a ripple value. The output voltage ripple is 1% or less of its DC component, and the converter is assumed to be ideal. Okay, so there is no here specific requirement to calculate, but I think when we ask about design, we have to design the inductor, the capacitor. If we can specify also the switches ratings, that's good. And because it's lossless here, Okay, so it assumes that it's ideal. That means there is no losses in the switch and inductor. But if we want to calculate that, we have to know the RMS values for each part. So now let's now start the solution. And again, I like always to remind myself by the schematic. So I have my input here, and it's in series with a inductor, and there is a switch here, and there is a diode, and also a capacitive filter, and finally a load. Okay, so that load is 50 ohm, and we don't know about L and C. We want to design them, and we have the V input here equals 12 volt, V output equals 30 volt. Okay, and the frequency 40 kilo, and the resistive load is 50. Maybe before going through details, we have to know the delta I value and delta V value. I think the easy one is the delta V output, because it's 1% of the output voltage. What is the output voltage? We know it, it's 30. So it's 1% of the 30 volt, okay? And that will equal 0.3 volt, okay? So we got a specific value. What about delta IL? Delta IL equals 80% of the DC component. What is DC component? We want to know the current going through that resistive load here. The current of the output here equals the voltage divided by the resistive load. And I think the output voltage is 30 divided by 50, and that will give us a value of 0.6 ampere. And now if we want to calculate the value of the inductance here, or the capacitance, we want to know the delta first, okay? So what is the delta value? We know that the V output equals 1 divided by 1 minus delta multiplied by V input, okay? So let's now take delta on a side by multiplying V output multiplied by 1 minus delta equals V input, and that will give us a value of V output minus V output delta equals V input. I will go step by step just to get the value of delta, and that means delta will equal V input, which is this one, and I will transfer that to the other side, minus V output, okay, and we'll divide it by V output, and that's all under the negative. That means delta finally will equal V output minus V input divided by V output. So this is the value of delta, and that can be calculated using the V output and V input value. So we have V output about 30 minus V input 12 divided by 30, and that will give us a value of 0.6. So we know the delta value, so we can now really use it to calculate the inductance value and also the capacitance value. So now let's do it here on that side. So we have the inductance value equals delta V input divided by F delta IL, and that will equal 0.6 times V input, which is 12, divided by the frequency, which is 40 kilo, multiplied by delta IL. But we didn't finish the delta IL calculation. By the way, we have started that, but we didn't finish it. So we have to make sure that we understand how we get delta IL. The delta IL, it says that it's 80% of the DC component. What is the DC component of IL? Maybe I mentioned that we have to calculate I output here, but that I output is not the DC component of the inductor current, because it's the DC component of the diode current, because that diode current supplies the output current here and also the ripple. So that 0.6 ampere here is the DC component of the diode current ID, but it's not the DC component of the inductor current. What is the inductor current DC component? I think we have to look at the circuit. So we have here the input current, I input, and it's the same as the IL current, which is the inductor current. So the DC component of my input current is the same as the DC component of my IL current. So how I calculate my input current? I think we have here an equation. The input current there and the output current there, we have a relation. So if I calculated the input current, output current, I can calculate the input current, and the input current is the same as IL current. This is the average current, okay? and that's the DC component of the requirement. So now I output should equal, from the equation there, 1 minus delta I input. Okay, so I input here will equal I output divided by 1 minus delta, and that will equal 0.6 divided by 1 minus delta is 0.6 as well, and that will give us a value of 1.5 ampere. And this is the average or DC value of my inductor current. See, if we are like memorizing the things, okay, so we will say that the output current is the same as the inductor DC current, which is wrong, not like the buck converter, okay? So now that 80% should be multiplied by 1.5 ampere, and that will equal 1.2 ampere. So this is the delta IL. So delta IL here is different from the output current. It's not the same, okay? So now we have here 1.2 ampere, okay? And the result will be 150 microhenry, okay? So that will also give us the continuous conduction mode, because we said that we want 80% of the inductor current, okay? So now let's go to the capacitor value. Again, we have to look at this equation here, and the capacitor value equals delta I output divided by F delta V output, okay? And that will equal delta is 0.6 times I output 0.6 again, divided by the frequency 40 kilo, and the delta V output, as we calculated here, it's 0.3 volt. Okay, and that will give us a value of 30 microfarad. And that's good. I think we calculated the inductance and capacitance value, but to make addition here and to specify the current of the diode and also the transistor, we have to know the inductor ripple. Okay, so we have here the inductor waveform will look like this. Okay, and the DC value here, we mentioned that it is this value, okay, which is I input value. This is 1.5 ampere. So 1.5 ampere, we have the ripple. The ripple is 1.2 ampere. So here we have the ripple. So let's write it here, 1.2 ampere. So that ripple, if we divide it by 2, 0.6 will be up. Okay, so let's now throw it here, 0.6 ampere here and 0.6 ampere down. Okay, so that 1.5, if I add 0.6 to it, I think it will be 2.1 here, 2.1 ampere there, and also at that value it will be 0.9 ampere. So I think my switch during the on time, because during the on time that current will go like that, and during the off time my current will go like that. So my switches, both of them, should handle the maximum and the minimum current. So let's go for the worst case scenario, 2.1. So the current, max current for the switches is 2.1 ampere. And if you want to select, we have to select more than this, maybe 3 ampere or 4 ampere. Let's look now at problem number 3. We have buck boost converter this time, and we have the following specification. V input 50, delta is 0.4, frequency is 20 kilohertz, the inductance and capacitance are given, and also the load. I think, yeah, most of the information are given. Assume that the converter is ideal, calculate the output voltage. And I think if we know the input voltage and delta, it's very easy to calculate the output voltage using this equation. So the solution is, so the V output equals delta divided by 1 minus delta V input, and that will give us a value of 0.4 divided by 1 minus 0.4 multiplied by 50 volt, and that will give us a value of 33.33 volt. And now it asks for the inductor maximum and minimum current values. We know that the inductor current will go from top to minimum, maximum to minimum. Okay, so it asks about this point and that point. Again, I think I forgot to draw the circuit. I think the circuit of the buck boost converter As always, we have here the switch, and there's an inductor there, and here we have the diode like this, and the capacitor, and also the load. Okay, in this case, our transistor here will switch the load during the on time, and my diode will take the current during the off time. Okay, so we want to know the ripple current, and that will give us the value of the maximum and minimum. So that's the ripple. Okay, so where is the ripple equation? I think this is the equation for the ripple, and let's now write it and see what is given and what's needed. Delta IL equals delta V input divided by F and L. We know delta, which is 0.4, multiplied by V input, which is 50, divided by the frequency 20 kilo, and the inductance given, which is 400 micro. So that equals 2.5 ampere. So the difference between the minimum and maximum is 2.5 ampere, but we don't know the average. If we know the average, I think we can add that ripple on top of that average, and we know the maximum and minimum. But that average in the on time, look at that. In the on time, the average of the input here equals the average of the inductor current. In the off time, the average of the inductor current equals the average of the diode current. So we want to use one of them to calculate the average inductor current. And I think in the slides we mentioned that. And we have here to be very, very careful. We can say always that the inductor current, average current, will go now like this in the off time, and the ripple will go through that capacitor, but the DC component will go through the output resistive. So I think my average or DC component of my inductor current is the same as my output current, but during the off time. So these are some other solutions and suggestions. So if I calculated my output current and calculated it during the off time, I can really know the inductor average current, and I can use it to calculate that level here. Okay, so I can say my output current equals my output voltage divided by the resistive load, and that will equal 33.33 divided by 20, and that will give us a value of 1.67 ampere. But this is my output current, but how much my inductor will support that or will deliver from that? I think my output current equals my inductor current, okay, but that is during just the off time. So I think we have here multiplication by the off time. Okay, so my inductor current will equal my output current divided by 1 minus delta, and that is 1.67 divided by 1 minus 0.4, and that will give us a value of 2.78 ampere. So that is the value of this level here. Okay, so please remember always how to think about the question to start analyzing it and to see what other approaches to calculate the value that you want. So it is not just one approach, you have many approaches. So this is the value, and I think from there I can calculate the minimum and maximum. So what is the minimum and maximum? So this is maximum is 2.78 plus the ripple, which is 2.5 divided by 2, and that value is 2.78 minus 2.5 divided by 2, and that will give us a value of 4.03 ampere, and that will give us a value of 1.53 ampere. And I think we're done for branch number B. Now the last one is the output voltage peak to peak ripple, which is delta V output here. Okay, so I think we can really use the equation delta V output equals delta I output divided by F and C. I think all of these known. 0.4 times 2, no, this is the output, 1.67 divided by the frequency 20 kilo multiplied by the capacitance, which is, I think, is given here 100 microfarad. 100 microfarad, and that gives a value of 0.334 volt. And that's it for question number 3. My advice is to try this and practice by yourself. Try to understand how many approaches we can solve the questions, and check if your thinking is right by checking the same answers here. And if you have more time, practice it another time before the exam as well. And I think you will grab all the concepts about how to analyze and calculate the values for DC to DC converters. Thank you very much for listening, and see you in the coming video.